Welcome, everybody. All right, so two quick announcements. So one thing is the Kaggle competition is done. So we will, I guess, post this on Piazza now. So these are optional 4 credit points. So basically the way it works is you have to, you can submit something, like, there's basically a data set. You get a training data set and you get the test points, but not the test labels. And then you have to train your classifier on the training data set and submit predictions for the test points. And then there's a leaderboard and you basically move up on the leaderboard. We submitted a bunch of straw men. And if you beat these straw men, the more straw men you beat, the better you get, basically. One thing is you're not allowed to infer the labels of the test points. So you could actually, these are actually images, I can tell you this right away. These are images of handwritten letters. Sorry, not handwritten, machine-written letters. So you could just take the test points if you wanted to and look at each one of them and label it by hand. It would be really boring and you would get 100% correct. But you actually have to submit the code at the end and you have to write a one-page write-up if you want to get it for credit, describing what you did. Yeah? Sorry? Can you use any library? Yes, you can use any library you want. So this is an open, you don't have to use Vocarium or anything, right? You can use any algorithm you want, etc. The only thing is you cannot use humans to infer that. You can also not go online and search for the data set or something. The data set is actually something we created, but you may find something else. So you have to use that training data set and that test set. Any other questions? Yeah?
When's the deadline?
Oh, when's the deadline? I believe it's May 10th. I'm not entirely sure. It's on the Kaggle competition webpage. It's the last day that anything can be due. Yeah?
Is it individual work or?
It's teamwork. And I believe the team can be up to 4 people. We specified it on the webpage. Yeah. All right. Oh, yeah. Last question. Yeah? Oh, sorry, you have to scream. Everybody else, please be quiet. Yes? So yeah, there's nothing with 3 people, if that's what you're asking. I just try to, increase my coverage. Okay, any more questions? All right. Okay, so last time, maybe next time I do pi. You can have pi number of people. All right, so last time we talked about decision trees. So the way we arrived there was we said we have a data set, and this data set may have different classes. And beforehand, the first thing we did is we did KD trees to speed up nearest neighbor search. And then we kind of realized, well, actually, if you build a KD trees, it would be good if you have leaves that are all pure, because in that case, you don't actually have to do the nearest neighbor search anymore. You can just look at, what's the label in that leaf, and then you just return that label. Now, when we build a KD, so decision trees are essentially the same thing as KD trees, right? You always split along one dimension, but you have a different splitting criteria. So with KD trees, what you did is we just looked at each dimension. We picked one dimension at a time, and we split such that the data set was exactly divided in half. And that was very easy, because you just have to basically look at the feature value along this direction, and you just split along the median. Right? So if you find the median, that's easy to find. You just count. And the moment you have half your data, you split there. So that's very, very simple. With decision trees, it's not so easy. Right? What you want to do, bless you, what you want to do is you want to find a splitting such that the 2 halves afterwards are as pure as possible. By the way, it doesn't have to be exactly balanced. So how do you do this, right? With KD trees, it was easy. We just split along the mean. With decision trees, it's not so easy. And therefore, it's a very simple trick. We just try out every possible split there is. That's the solution, right? So what you do is you just look at every dimension and at every single split you could make. And you try out every single one. Right? So there's D dimensions. In this case, there's 2 dimensions. There's N data points. There's D times N splits. Actually, it's N minus 1 to be technically correct. Because you only split between 2 points. Right? So basically what you did say, I would like to split along this direction. I try that dimension first. Then I look at every single data point. This here is the projection onto this direction, which is just that coordinate. And I try out a split between any such data points. So we need a second ingredient. The first ingredient was how do we find the best splits? The first thing is, well, okay, we just try out every possible split. That's great. Now we need one more thing. We need to be able to evaluate how good a split is. And for that, we need an impurity function. And last lecture, we went over two of those. Gini coefficient, Gini index, and the entropy function. And so the way this works is quite simple. Let's say we evaluate this split here. We want to know how pure is that split. And so basically what we're doing is we look at each one of these subsets. So we take the entire set and we divide it in two. This here is the right subset, this here is the left subset. And what we compute the following. We have this function h, which for a set computes how pure that set is. And we had two different ones, the entropy or the entropy, or we had the Gini. Gini said we sum over k, pk 1 minus pk. And entropy was we sum over k, pk log of pk. We do this negative. So that's the only difference. This here is Gini. This here is entropy. And so both of these functions have one thing in common. They kind of, if, pk, let me just define pk, remind you of what pk is. If for each one of these subsets, let's say I have, this set S, then I define sk is the set of all the points x element of S such that y equals k. So all the points with a particular label, then I say pk is the fraction of points that have that label. All right? So when I do a split, what do I have to do? I look at each set individually, and what I do is I compute what's the fraction of points with a given label. I compute this for every one of the labels. And then I compute the impurity, either using this formula, it's entropy, or using this formula, it's Gini. Now I get an impurity for the left-hand side and the impurity of the right-hand side. And how do I weigh these two? Just based on how many points are in each side. So if this here is my left-hand side, this here is my right-hand side, then I say the impurity of the split is h of s left times the fraction of s left divided by the total plus h of s right times the fraction of the right. Okay, any questions at this point? Yeah?
How does this work for regression?
That's what this lecture is about. Good question. Any other questions? Yeah?
Also, so we made the assumption that if you went into a leaf, you probably wouldn't change your nearest neighbor, even if you were, if you're probably not going to change into another, have a nearest neighbor.
It's the approximate nearest neighbor, yes, yes.
In practice, does this work out well enough?
So, in practice, the decision trees are so much faster if you don't have to store the data points, that it's actually well worth it. So yes, so by the way, I'm still standing with this. Decision trees are lousy algorithms, right? But if you bag them and boost them, they become really good algorithms. And that's what we will talk about. So because they're now so cheap, we can actually compute many of them and average them. And that's essentially bagging and boosting. Okay, any more questions? Okay, raise your hand if that's clear now. Okay. All right, so now comes a little quiz. When you consider a split, what is the complexity of evaluating this formula? Complexity, what I want to know is this big O notation, right? So how many in terms of dimensions, in terms of samples, how many operations do I have to make in order to compute the impurity of a particular split. All right, so you and your neighbor, I give you a few minutes, try to figure it out. All right, who figured it out? Any guesses? I make a split, and I want to know, so now given that split, I now basically divided the data set in left and right, and now I have to compute this impurity to know how good that split is. Right? So basically I have to compute the impurity on the left-hand side, the impurity on the right-hand side, and I have to weigh it by these two terms. What fraction of the points go to the left, what fraction of the points go to the right. And I have to do this for every single one of the splits, so I have n times these splits. And now the question is, what is the computation of evaluating one particular split? Who has a guess? So what is the computation of what are the computational requirements? What's the computational complexity of computing this term here for a particular split? So I have a split in left and right. What does it cost me in terms of number of classes, number of data points? Any guesses? Yeah?
Is it k times n?
So yeah, so I guess I called it last time, I called it C. So k is number of classes. So this function SHFL is actually, let's say it's the 1 to capital K or C, pk log pk. Right, so that's definitely a sum that goes over k, over all classes, right? Capital K classes. So we definitely have, let's call it capital K. Why not? So we have capital K classes, and then what was your guess?
Just k times n.
Times n, and why n?
Because you have to go, for each class, you have to go through the entire data set, checking to see which one goes where.
So that's right. So you have to go through the entire data set, see which one goes left and which one goes right. And you also have to go, then within each subset, you have to basically count how many, for every class, what the fraction of points of that class, right? So you have to compute your pk, right? So pk, ultimately you go over all the data points. So it's n times these splits, and each evaluation costs k times n. So that is, the complexity is d times k times n squared. Okay, yeah?
So it seems to me like the split is binary. How would this work?
That's not no problem, right? So you always split the data set into two halves. And this function here just sums over all your classes. There's a k. So this is actually, there's nothing here that's about binary. You keep splitting, and so the impurity function goes over multiple classes. That's fine.
Oh, so you're just saying you want sectors where permissible class.
That's right. What you want to do is you want to find leaves that have only one particular class, right? But you could have many, many different classes. Not a problem. Okay. Raise your hand if this makes sense. Not many. Okay, who understands big O notation? Okay. This, by the way, was invented at Cornell University. Big O notation was a Turing Award. Yeah.
I just randomly thought of something, but if you use the hash table, wouldn't you separate everything into classes in one hash?
Oh, we're going to make this a lot faster. Don't worry. So, one more time. What this here is basically how much work do we have to do, right, in order to find a good split. And so, what do? We go over all d dimensions, and we try out every possible split. If you have n data points, you can kind of split before each data point in that dimension. So we have n times d possible splits that we want to evaluate. In order to evaluate a split, to see how good it is, we have to do that much computation. We have to basically go over all our data points and divide them up into k classes, and then we go over each k class and we express this term here, which is basically says the entropy is actually negative. We just have to sum up over all these k classes and compute this term. Okay? But estimating all these p's, or the fractions for each class, costs us order n because we have to go over each data point and see which label it is. Does that make sense now? Raise your hand if it makes sense now. Okay. All right. So it turns out this is the computational complexity. That would be pretty bad because it's quadratic. That means if your data gets twice as large, it takes 4 times as long. Right? So that's actually a pretty slow algorithm. You couldn't run this over large data sets. Turns out there's a very good trick in how to do this much, much, much faster. And that's the following. Imagine I want to evaluate a split, but I've already evaluated the split before. And please pay attention now, because that's exactly what's going to be the question 3, I think, in your next project. So if you implement your tree, the first thing you can do is you basically implement it exactly like this. You chart every single split, and for every single split, you compute the purity, and then you just pick the one that basically minimizes your loss function. That's it. You remember that split, you output that, and then you build the next split. That's how you build the tree one by one. So basically, you have your original node, you find the best split, that gives you 2 subnodes, and then recursively for this one, you find the best split, and for this one, you find the best split. But each one of these requires you to go over the entire data set if you implement it naively. But if you're smart, then you do the following. You go through these splits one by one, and you will realize one thing. Every time let's say I've already evaluated this split. Now I move 1 to the right. This split I've already evaluated. Now I want to evaluate this split. The only change is that one cross moved from the right side to the left side. Okay, does that make sense? Otherwise, these splits are exactly the same. The only difference is this guy, for this split, is on the right-hand side. For this split, it's on the left-hand side. Okay? So on the right-hand side, my fraction of points, my counter of points with the crosses, goes down by 1. On the left-hand side, it goes up by 1. Okay? That's a constant operation. So if you do the splits one by one, then actually evaluating the splits only costs you order k. So you can actually get rid of this factor n. So you don't need this factor n. Because you basically can reuse all the computation from the previous split. You just count. Now when you move 1 to the right, you basically say, okay, well, exactly 1 point moved over. So you just keep a counter how many points you have of each class on the left-hand side. And the moment you move 1 step to the right, only one of these counters goes up. That's it. And then you basically have, again, all these probabilities for every single class label. So that's how you implement the project. And that actually now makes this algorithm really, really fast. Now it's linear with the data set size. So now if your data set size doubles, the algorithm is only twice as slow. right? Not 4 times as slow. That makes a huge difference. Any questions? Yeah? You do have a log in there for sorting. Yeah, I kind of put that under the rug. Yes. Log n is 30. All right. Any other questions? Yeah?
I was confused about the initial setup. I guess what I was thinking was what you just went over. So in the initial one, you're saying for each time, you're just classifying everything for each split. Like, well, I was confused why the k and like the n was.
Why the m was in there? Yeah. The question is initially why was the n there? Because you have to compute the pk's. You have to know what's the fraction of positive points on the left hand side, what's the fraction of negative points on the left hand side. So you have to, these pk's are computed from these data sets, right? SK, so these counters. How many points are positive on the left hand side, right? So you have this for the left hand side, say, right? What I'm telling you is if you move the split, that can only change by 1. So you just keep a counter here, how many positive points you have on the left hand side, how many positive points you have on the right hand side, and you just decrease one and increase the other. Does that make sense? Oh, I see. You're okay. Good, good. Well, that's good. Okay. Any more questions? All right. Let me get to Arthur's question then. Arthur's question was, how do you do this for regression? Right. So imagine you want to do regression, and so in regression we don't want to classify. We don't have classes, but our classes are actually real numbers. So for example, you want to learn a function that looks like this. Can you use decision trees for regression? Right? And the answer is yes, absolutely. It is called regression trees. And actually, if you see CART, they're often called CART trees, classification and regression trees. So from the beginning, they were actually considered for classification and for regression. How does this work? It's very, very simple. You do exactly the same algorithm. The only thing is you don't use entropy, or you don't use the Gini coefficient. Instead, you use the square loss. So you say, my loss function for a certain set is the following. This is some 1 over x comma y element of S. And you just compute y minus mu squared, where mu equals the average, the mean point of all the labels in S. Okay, so here's what you do. For a set, you say the impurity of that set is how close everything is to the mean. So for a set S, you compute the mean, the average label in that set, and then you say, on average, how far am I off from that mean? Does anyone recognize this formula? Sum y minus mu squared. It's a variance. That's right. It's just the variance on the right and on the left. That's all there is. Right? So in practice, if you do this, what happens? So you have your data points here, sampled from this function. So what do? You take this function, you split it somewhere, and you estimate everything on the right by the mean, and everything on the left by the mean. You say, my function kind of looks like this. Right? Just 2 straight lines. That's a lousy approximation of that function. Right? But that's okay because you can keep splitting. So you split again. You say, okay, well now I take this mean and this mean. Right? And here I split again. Take this mean and maybe this mean. And then I split again and again and again. And at the end, if you do this many, many times, what you will get is a function like this will be approximated by many such, straight lines, basically. Okay, so each leaf basically just predicts one value. And you basically predict, you split your space repeatedly, and then for any given x value, all the points that basically fall into one interval, you just predict the same label. So it's not a smooth function, but actually works surprisingly well. Any questions? What you need to do on homework 7 is you have to show that this update can also be computed incrementally. So if you basically move your splitting point one to the right, you can also update the mean and you can update this loss with just a very small computation. So you don't actually have to always compute the mean on the right, the mean on the left. Because the fact that you know this 1 point moves to the right, you basically subtract a little bit from the mean on the right, add a little bit on the mean to the right, left, and then you just clean up these factors. And the way this works is by just summing out, writing this as y squared minus 2y mu plus mu squared. And then you keep track of each one of these terms. That's in some sense, that's a big hint for homework 7. And so you need to do that first before you implement it in the next project. Any questions? Yeah?
So when we had the concept of pure leaves, we knew to stop when we had a pure leaf, but we're not going to get something with variance 0. So how do we know when to stop?
Ah, very good point. So his question is, we keep splitting, and you can always keep splitting and improve your result, right? So when do you know when to stop, right? Because this, you will never have 2 points that are exactly, or very rarely, all the leaves with the same value. And that's absolutely correct. And what you essentially do is you trade off, you basically just say you only grow to a certain amount of depth, or you stop when there's m points in your leaves. That's what it is. Very good question. Any more questions? Yeah? Oh, you can use any loss you want. Right. It's actually, because you try out every single split, right? You can even use losses that are not differentiable, right? Which is awesome. Which is really, really powerful, right? You can have a really complicated loss if you want to. You're absolutely right. Right? The mean is just, square law is just neat because you're actually computing the average on each side, but you can use any kind of loss. Very good question. Okay, any other questions? All right, so decision trees are in some sense a very different way of doing machine learning than empirical risk minimizations with these linear classifiers. But it's somewhat analogous, right? You also have a loss function. You minimize that loss function. You don't minimize it with gradient descent. You minimize it by repeatedly splitting your data and changing your predictions. And you also have a regularization term. And the regularization that basically says, don't make your solution too complex. And in empirical risk minimization, we said it's lambda times the square norm of W, for example. That was the one regularizer on SVMs. Here we typically say, we just limit the depth of the tree. So we basically say we want to find a tree that minimizes our loss, subject to the constraint that our tree can have at most depth of 10 or something. Okay? And so this depth is, what you have to balance bias variance trade-off. And what I showed you last time is this little demo where you could see the training and the test error. By the way, what people typically do, so in our homework project, we just say we limit the depth of the tree. A better thing to do actually is to limit the number of nodes in a tree. To basically say, well, a tree could look like this, where you actually have a split here, and then you have 2 more splits here, maybe something like this, right? And that's only a complexity of 2, 4, 6, right? That works a little bit better than just limiting the depth of the tree in practice. So if you take the depth of your tree, then the training error as a function of depth will always go down, and it will go to 0 eventually, right? Unless you have 2 identical points that can't be split anymore with different labels. And the reason is because you can keep splitting until every single leaf is pure. Okay, until you basically that must mean you have 0 training error. Even in the regression case, right? As was just pointed out earlier, you can keep splitting until you make 0 error anymore. Now this is the training error. The testing error looks like this, right? And so here is the problem of decision trees. That it's very hard to find the sweet spot here. And the reason is empirical risk minimization with lambda. Lambda can take any real number, right? Decision trees, this has to be an integer. So you can either have 3 or 4, right? But you can't have 3.3, it doesn't really work, right? Because you can only go in these integral steps, right? You basically keep going down and then you go up, and then there's not much wiggle room here. So it's very, it's the sweet spot, basically, there's some depth that actually gives you the minimum test error, but it's not a very good way to balance, it doesn't allow you to have a fine-grained, sensitive analysis of what the best trade-off is between bias and variance. And that is, in some sense, the downfall of decision trees. That's why, in practice, they don't work very well. Because, there's basically really only one setting, and that may not work all that well. Right? What you would really want is something in between here, but it doesn't exist. There's no notion of that. So, what we'll do the next 2 lectures, and actually starting now, is fix this. So, decision trees have a bias and a variance problem. Right? Here they have high variance. Here they have high bias. And finding the sweet spot is really, really hard. So what we will do is we will find the sweet spot with a different way. Not changing the depth of the tree. We will either basically make the depth really small and admit that we have a bias problem, and then combat the bias another way. Or we will make the tree really, really deep, and then we have a variance problem. Then we are memorizing our data set and overfitting until the cows come home. Right? But that's okay, because we can actually address the variance problem in another way. And that's exactly what we'll do now, and that's called bagging. All right, so remember what we will do is we will grow really big trees and just say they have a variance problem, and we try to reduce the variance. And so actually the way I will describe bagging to you is independent of the classifier. And actually bagging is something you can use with any classifier that has a variance problem. And please remember it. It's something that somehow people have forgotten over the years. It's an algorithm from the 90s, early 90s. Invented by Leo Breiman, Berkeley University. And it's really a fantastic algorithm. It's ingenious and it works really, really well. So please keep it in mind. When you have a variance problem, like when you go out in the real world, you use machine learning on your data sets. Analyze the problem you have. If you have a variance problem, use bagging. It's amazing. So here's how bagging works. So if you look at the notes, who didn't get a note? Almost everybody. Sorry, that was a printer problem. The printer died once again. It's not an excuse. I'm not, it's not that my dog ate the homework. It really dies, apparently quite a bit. Okay, so you remember that bias variance decomposition. So the error decomposes into 3 terms. Noise, bias, and variance. And variance is the following. This is just a reminder. So we have HD of x Can anyone tell me, remind me, what's H bar? What's HD? Who remembers? Yeah?
H bar is the prediction used by the error classifier, and HD is
That's right. So HD is, if I have a training that said D, HD is the classifier I learn. This expectation is also over D and over X. And H bar is the expected classifier if I integrate out D. And so if you have a variance problem, that means this term here is large. So it means that your classifier is quite a ways off from the expected classifier, right? So if you had a slightly different data set, you would get a very different answer. And that's exactly what you get with decision trees. Can anyone tell me why? Why is that happening with decision trees? Why do they have a variance problem? Why do you get a different, if you had a slightly different data set, you would get a different classifier. Yes?
Well, maybe because this completion is like half all the time, so it's one data point, like separately can actually change out over the loss and like go different stuff to each completely.
Yeah, you're right. So basically you split on the data points, right? And you keep splitting until you make no more mistakes, right? So if at the end you will get everybody right, but all these low-level splits, they're very data-specific, right? So if you had different data, you would get very different splits. And you would split on different dimensions, right? And that makes completely different classifiers. All right, so decision trees have a variance problem. So how could we fix it? And here's an ingenious way of fixing it. Instead of just saying you have one data set D, I just ask my uncle, who's a magician, and he gives me many different data sets. D1 to DM. Okay? And I train a decision tree, classifier on each one of these M data sets. And then what I do is I say my final classifier, H, is just the average of those. Let's call this a DJ. Right? So, I ask someone to give me M data sets. Let's not think about how I get those M data sets. But if I had M data sets, then what I could do, I could train a classifier on each one of these M data sets, and I could average the results. And why is that a good idea? Well, if M gets large, then this here becomes exactly H bar. Okay? By the weak law of large numbers. Right? Because these are basically IID drawn, these are basically my random variables here. And as my classifier becomes closer and closer to H bar, this becomes 0. So if I had access to M different data sets, and I could make M really, really large, then I could make the variance arbitrarily small and go to 0. Okay, and because I have a variance problem, my error is dominated by this term, so I can make my error really, really small. What's the catch? Why isn't everybody doing this? Yeah? So I guess what you're implying is, that I take my data set D and divide it into M data sets. I actually thought that, somehow miraculously my uncle gives me M times more data. But you're right. So the answer is you don't actually have those data sets, right? And one thing you could do is you could take your data set and divide it into M small data sets, but then you're totally right. Then you're actually trading that off, And actually you're also making variance worse because your data set is smaller, right? In fact, you can't make M infinitely large because in the extreme case you only have one training data point, right? So you can't do this. right? Because you don't have m data sets. You only have one data set, right? And here comes the ingenious thing that bagging does, right? Bagging does, well, never mind, right? Let's just keep going. Let's just pretend we have these m data sets. And in fact, we can make them up. And here's the trick. Has anyone heard of bootstrapping before? Right? Bootstrapping comes from the, Baron von Münchhausen, who you've probably not heard of. But he was a big aristocrat in Germany, and he was a big liar. And one day he got stuck in the snow, and they asked him, how'd you get out? And he said, I pulled myself up on my own bootstraps. That was his explanation. Obviously, that's not possible. He was lying. But the name stuck. So what we will do is we will, this will make a lot of sense in a minute. We will actually create these data sets out of the original data set. And here's what we do. We say, okay, we take our original data set D that we have, and now we create m different data sets with a little magic trick. We sample n points with replacement. So sampling with replacement. With replacement. And we do this m times, so that we get D1, Dm. Okay, so basically what we do is we take n points, we fill this data set up, and every time, one point at a time, and every time we roll a die and pick one data point here at random. Now the important thing is that we do it with replacement. And because we're doing it with replacement, these data sets are not all the same. Because you can pick, so with replacement basically means you can pick the same point over and over again. Right? In the extreme case, this data set could just consist of one data point, repeated n times. Right? The chances are very small. The chances are 1 over n to the power of n. Right? But it's possible. Okay? So what we will get is we get m different data sets that each one of them consists of data from my original data set D. Any questions? Raise your hand if that makes sense. Okay, awesome. You will have to implement it in the next project. All right. So now if we do this, right, we can basically now do the same thing. We just, on each one of these data sets, we train our classifier, and we get H1, H2 to HM, and we average them. Now there's one thing. As m goes to infinity, this does not become the average classifier. Can anyone tell me why? Without looking at the notes? Which property of the weak law of large numbers is violated? Yeah? That's right? So they're actually not independent. Right? If I tell you this data set and this data set, this data set, you get a very good idea of what's going to be in the next data set, because this is drawn from the same points. It's the same points over and over again. Right? There's only so many points that go around. Right? So you have these m functions. That's okay. Right? So this is no longer holds, but it holds approximately. Now, given some assumptions, it kind of holds. Right? Or at least say, this term still goes down. So they're no longer independent, but one thing we can show is that these data sets are still, so there's another problem that we could have. And that's if these data sets are no longer drawn from the original distribution. So our distribution D is drawn from some distribution P. One thing we need to show is that these distributions are, these data sets are drawn from the same distribution P. What's the time? Yeah, let me do it real quick. Turns out you can prove this. Relatively easily. And here's the proof. So what I want to show is that each data set di, or dj, is drawn from the original distribution P. And so here's what I want to say. Let me call the following distribution Q. Q is a distribution where I basically pick a data point from this data set uniformly at random. Sorry. Q is a distribution from which this data set dj is drawn. And I want to show that's the same distribution as the original data set, P. And so here's, so what's the process of Q? Well, the process of Q is I first draw a data point into my data set D, and then I draw n of them into my data set di. Okay, that's basically the process. That's a process. You know what, why don't I just show you a demo and I do this next lecture? I mean, there's people give me this look like, oh my gosh, you have 3 minutes left, come on. I generate a data set. Should we do something hard? Any suggestions? What should we do?
Alternating points in a checkerboard fashion.
Oh, that's so easy for this regression tree. You can just split horizontally and vertically. It's like a spiral. All right, okay, spiral. But spiral is actually really, really hard for decision tree, right? There's like this, you know, decision trees' nightmares are made of spirals. Oh. Okay, this is my spiral. It's a good spiral. Okay, good. Here's my spiral. It's like yin and yang. Okay, so what I will now show you. Oh, yeah, you can actually see it. Okay, good. So this is actually when I average many, many decision trees. And never lets me down. All right. And what you see is that here's actually, you see the average of many, many trees, right? So on average, basically, right, it actually covers this very, very nicely, that basically where this positive mass is, right, where the x's are, actually on average, these trees are doing very, very well, right? And also each one of them looks very, very different. Actually, let me show you one more demo, actually. I can actually have even random forest variance demo. What one's? Okay, one more time. I do one more. Oh yeah, here we go. This is a slightly different data set. And what I have here, I show you different decision trees that I learned in a slightly different data set. Basically, doing bootstrapping. And what you see in the bottom now is the forest, right? And so one thing you can see very, very nicely, look at these vertical lines here, right? But a decision tree basically makes some wacko decisions, right? Just because it splits here, all of this is blue, right? And here it makes these long vertical lines because of one point, it kind of takes this entire area and makes it blue or red, right? So that's the high bias. That's where the high variance of decision trees come in, because they always make axis-aligned splits. They kind of always cut the entire space in half, right? But if you look at the forest, on average, actually, this is very well behaved. And you see this kind of, this is kind of spiral Lee data set here that you actually comes out here very, very nicely, right? And so it turns out random forests actually very, very, so these random forests are basically decision trees of forests, average decision trees, are very, very good classifiers, right? So you can take some really bad classifier that is, because you know it has a variance problem. And I think that's the key thing I want you to take home from this, right? We took a crappy classifier, but we knew it was a variance problem. We could address it with bagging, and then we got a really, really good classifier, right? And so please remember this when you do data science later on in your life, right? When you analyze and you have a variance problem, if you do bagging works really, really well. It has some very nice advantages that we will get to next lecture. All right, see you guys.